Membrane permeability. The plasma membrane, or the lipid bilayer of cells, is permeable to some substances, they can go through, and impermeable to other substances, they can't go through. And they are, to some substances, more readily to go through as other ones, and that they are selecting which come through is called selective permeability. But there are still ways to come through. Water can come through, and that is a bit strange, but first, why it's strange? Because things like uncharged and non-polar molecules, they can pass through. Carbon dioxide, oxygen, steroids. And so they're permeable to them. And charged things or polar molecules like glucose or also ions, they cannot pass through. Water is charged. Why can water pass through? They're saying that it is probably, or maybe, or it is thought because of it, because all these glycolipids and phospholipids on the outside of the lipid bilayer, they're moving all around the whole time. It is not firm. A cell has not a firm part of the outside. These are just these phospholipids standing with the phosphates and the fatty acid tail, and they're all the time changing places, all the time. So one can go just in. And with the needle, for example, for fertilization or for cloning with dolicho sheep. So one can go just in, and the idea is now water, even though being polar, can just go in and through small gaps when they're changing again. That's the idea. There are some possibilities for other things to come through. There are the channels, and these channels are letting through only a specific substance, or also selective channels, letting them one substance through, only one specific one. A cell is oftentimes multiple different ones of these selective channels, so that through each of them can come a specific substance in. Or, for example, the transporters, they're taking something and like a snake, do they bring it in. And there is also the vesicular transport, with that also macromolecules, so macro, big molecules can come in, or other things. And that is not explained on that page here, it's later on explained. It has something to do with the ligand cord, that is the specific substance which can come to that receptor there. The ligand, some substance, comes into the receptor, stays from there. That would be just the receptor, and because it is there, it changes the surface of the cell. It changes the cell because the cell has now that ligand docked onto it. It changes the cell, but now the vesicular transport can happening. The clathrine-coated pit around the cells, they can start to go around and pinch them off, and now it's taken in. That would be vesicular transport, and that way also macromolecule or something could go in. And that is according to Gerard Tatoga and Sandra Grabowski's Principles of Anatomy and Physiology book on the page 64-65, but this is no substitute for medical knowledge and also for medical advice. I'm back. I'm trying to learn cytology. Today, membrane permeability, and after we've done it, we're going to do wrist training. And if you participate in the wrist training, then it's at your own risk. Membrane permeability. I don't know what permeability means. A membrane is permeable to things that can pass through it and is impermeable to those that cannot. So permeable means it can go something through, impermeable means it cannot go through. Air is permeable, walls are impermeable. Permeable. Okay, although plasma membranes are not completely permeable to any substance, they do permit some substances to pass more readily than others. So plasma membranes are not completely closed off. Some can pass faster through it, others slower. This property of membrane is called selective permeability. They're selecting who comes through it how good. The lipid bilayer portion of the membrane is permeable to most non-polar uncharged molecules such as oxygen, carbon dioxide, and steroids, but is impermeable to ions and charged or polar molecules such as glucose. So non-polar things, for example uncharged molecules like oxygen or carbon dioxide or steroids, they can just pass through it. But not ions and charged polar molecules like glucose, they cannot pass through it. It is also permeable to water. An unexpected property given that water is a polar molecule. Water is polar, H2O. Water can go through. Even artificially made, pure phospholipid membranes are permeable to water, which is thought to pass through the lipid bilayer in the following way. Okay, water can pass through the lipid bilayer. The idea is that it happens the following. As the fatty acid tails of membrane phospholipids and glycolipids randomly move about, small gaps briefly appear in the hydrophobic environment of the membrane's interior. Water molecules are small enough to move from one gap to another until they have crossed the membrane. All these glycolipids, they are like air balloons or like lollipops or something. They're having at the top the one polar, non-polar particle. The fatty acid tail is whatever it is something. They're moving about, they are changing all the time places, and sometimes there's a little error and then the water can come in. Water molecules, transmembrane proteins that act as channels and transport increase the plasma membrane's permeability to a variety of small and medium-sized polar and charged substances, including ions that cannot cross the lipid bilayer. So as we heard, the lipid bilayer doesn't let through charged particles or ions through it. But they are transmembrane proteins. And these proteins are very selective. Each one helps only a specific molecule or ion to cross the membrane. Macromolecules such as proteins are unable to pass through the plasma membrane except by vascular transport, discussed later. That basically said with the membrane layer that some things through, others not, some go easier through, others harder. And water can go through it because all these glycolipids, like air balloons, they're sometimes going a bit, they're changing places. Whenever they're changing places, there's a little time left for water to come in, and there seems to be transmembrane proteins. We haven't had them, but it could be something like there are some proteins going from one side to the other one and taking them the other ones with them. That way also charged particles can pass through it. Charged particles cannot pass through it so easily. Okay, that was the membrane permeability. In the next part we're going to read on about the gradients across the plasma membrane. Maybe they're going to explain it then. Transport across the plasma membrane. There's more. That was a cytology part. If you were here for cytology, you can go ahead to the next part of cytology that we're going to read on. If you stay here and participate in the wrist training, it's at your own risk. Good and still said. Arms up with fists. Bring them down. The spotlight. And the flashlight fists into the inside and outside. Flat hands, the magician, inside and outside. And flat hands and open and close the pancake flipper. We're having 3 rules. The first rule is that we're stopping immediately as soon as there's pain. Arms out, the T-Rex in the morning and down. The second rule is that we're going only as far as we can go with a little bit of it. Fists and the quadrangular castle are connected inside. Up. And the third rule is that we're not overdoing it. We just want to strengthen, not to exhaust. You can take a break whenever you want. And the crab, not the frog, the crab anxious to have fever. Hand to the fists and bring it down. Press 1 second. And on the outside. And on the other side. Next. And on the other side. Now the T-Rex in the gym, you can use a tennis ball or without one, just make a strong fist. Or press into the tennis ball. Release. Press. Release. Press. Change. Press. Release. Press. And now the cautious big bang. Fingertips of one hand on top of the fingernails of the other. Go slowly. Close. Change. Out slowly. And close. And the field daisies no synthesis director fists. Open. Close. arms up, the fists down into flexion, down, and again up, and around, down, and again up, and again turn it around, down, and up. You can take a breath if you like. The frog, anxious to a fever. Now the frog, testing with water temperature. Hands down with flat fingers, up with strong fists. Down, and up. And now the bicycle bridge, flat hands, bended knuckles, up again, bended knuckles, up. And hands up with strong fists into flexion and out into extension. Flat fingers. Up strong fists flexion, out extension flat fingers. In strong fists flexion, out extension. And the claw, flat hands, make claws, spread the fingers, up, close, close, up, close. And now, the I6, flat hand, bend the knuckles and press into all four fingers. Other hand, bend the knuckles, press into all four fingers. Up. And the rocket boosters, launchers, long arms, strong fists, flexion, and extension flat fingers. Again in, and out. And now go with moderate pressure over the middle part of the arm, and on the other side. And that was the wrist training. I thank you very much, and until next time.